size, which is thankful. We'll get to the nuts and bolts here momentarily. Now, the reason I keep bringing these data sets up to you guys is if you look at the units on these things, heights of American women, you cannot count those. You have to measure those. LDL readings, you cannot count an LDL reading, you measure it. It's usually milligrams per deciliter, I believe, is the unit used. IQs, that's not counted, that's measured too. Guess what else is measured? A whole bunch of other things. Here's a few things that I found that tend to be bell-shaped. Now some of these are discrete, but most of them are continuous. Times of eye contact with schizophrenic patients, weights of coins, actual volume of a 15-gallon gas tank in a car. There's fluctuations in those things. Yeah, there are 15 gallons on average, but then there's pluses or minuses around that. When you buy a nut and a bolt at a hardware store, generally, if you buy a 1/2 inch bolt and a 1/2 inch nut threaded the same way, it should turn in the nut and grab and not slip, unless it's a poorly machined bolt. But every one of those nuts in that tray is a little tiny bit different than every other nut in the tray. But they're within a certain level of tolerance from what it should be, which means they'll all work. Just like Legos. I looked at the precision. I went to Lego Land with Max not that long ago. The blocks, the Lego blocks, so they'll all snap together. I have my sets from the 80s. He went to that Lego movie, the little blue spaceman. He came in and was like, Daddy, there was a blue spaceman. I'm like, dude, it's in the attic. He's like, you have it? I'm like, yes, I was a child in 1986. I pulled it out, his like eyes lit up. He's like, oh my God, you have Benny. I'm like, I got a blue spaceman. It wasn't that big of a deal in the 80s. I guess it's a big deal because it lasted 30 years. But Lego blocks from the 80s snap together Lego blocks from this day and age. He could take his Star Wars Ewok village and put it together with the Space Cruiser Set 7269 from 1982, and the blocks work great. Why? Because of the tolerances they built in. Every one of those blocks is different, but it's not so different that they won't click together. Please, Nathan.
I have a set of Mega Blocks, and they have a much higher tolerance or a much lower tolerance.
Yeah. Yes, they do! Some of them work with Legos, some don't. Much lower tolerance. You're right. You're right. Exactly. Legos tolerances are, well, Legos are made in, I think, Switzerland or Switzerland, I believe. Denmark, thank you. Thank you. Very, very tight tolerances in Denmark. Good. Lego means play well in Danish, I think, right? I think that's the translation of the word Lego, play well, which is great. Anyway, that's not the only thing. Check this out. Have you ever been, why are you not switching? Oh, there we go. Oh. Have you ever been to Amsi? So check this out. Maybe you've seen this at Amsi. There's Max. He's going to explain it to you here in a second. Hang on. What this is, it's a little tiny series of little plastic balls that get dropped in at the top of that box, that plastic plexiglass box. It drops down. On the way down, you can kind of see it. It's bouncing off little pegs that are arranged in a grid. And it's, well, that's what I explained to you. Hang on.
Oh, yeah?
Mm-hmm. Did you get that? Well, let me explain it to you. What he's saying is, they fall in the middle. They fall in the middle. Where do most of them land? In the middle, but not all of them, right? Some land off to the left, some land off to the right. Fewer, but some land further off to the left. Further, but fewer land further off to the right. Do some land off at the tails? Well, clearly, because they're actually landing over there. Every once in a while, you'll see a little one fall in. But not too, oh, there's one right there. So you see what's happening? It's very, very rare. Here's a later look at the exact same experiment. So what's happening over time is, there's my wife explaining it now. What's happening now is over time, you're beginning to see this beautiful thing filled in right here. Now why would that happen? Why would that happen? I mean, it seems random, doesn't it? It's the ball's hitting things on the way down. It's the butterfly effect. It's bouncing off. You can see it there. Bounce, 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 bounce. But some of them shoot off that way. And some shoot off this way. What the hell's going on? Say that again!
There's a 50-50 chance of falling each direction
every single time, thank you, Nathan. That's my explanation too. That's how I explain it to everybody. Every time that ball hits a post, it has a 50-50 chance of bouncing off. I'm going to go back and run a little bit and pause so we can point and show you what I'm talking about. So here, okay, pause. Okay, so if it leaves the hopper at the top and hits the first post, which is right there, half of them then go to the right, half of them then go to the left. Then it hits the next pin, wherever that is. Half the time, arguably, it goes to the left, half the time it goes to the right. You can adjust that a little bit. There is some physics going on too. If it's coming in from the left, it's got a higher probability of going back left just by where it's coming in. But statistically, it ends up being roughly half and half on average over time. Because not everything comes in exactly straight. There's all kinds of little tiny variations in the motion of those balls. So essentially, a left and a right turn are 50-50. Well, that's like Max putting his Crocs on if he's guessing, isn't it? Most of the time, you're going to land in the middle. In order for it to land way the hell out here, you have to keep taking right turns. What's the chance of taking right turns if you're flipping heads and tails on a coin? That's like flipping a coin and getting heads all the time. Does it happen? Yes, just not that often. Same as flipping tails all the time, which is over here. Now, why does it follow this beautiful bell-shaped distribution? That is a trickier question, which I have a solution to. It's not a good question to answer in class. It'll put you right to sleep. If you're interested in why the actual bell shape happens, I've got an enrichment paper on the enrichment page of the site. You can, by all means, if you have trouble falling asleep tonight, read that. It'll put you right out. But it actually falls down, believe it or not. And you don't have to believe this, of course. I'll show it to you. Back in the day, Germany, before they were on the euro, were on the mark system, Deutsche Marks. This was their equivalent of their $10 bill. We put useless people like presidents on our money. We put Lincoln. He wasn't useless. He was wonderful. I can't remember who's on our $10 bill. Franklin. Franklin's 100. Lincoln's 5. Jefferson. Jefferson it is. It doesn't matter. Jefferson was a good guy. They put mathematicians on their money. Why? Because Germans are awesome. They put Carl Friedrich Gauss on the $10 bill. And not only that, they put a friggin' bell curve on the bill. Not only that, they put a bell curve. Zoom in on that bad boy. There's the equation. Not only the curve, but the equation is on there. 1 over sigma root 2 pi e negative x minus mu squared over 2 sigma squared. That's what I explained in the paper if you want to see it. That is the reason the curve is shaped the way it's shaped, is because of that equation. If you care, and I don't expect you to. The paper exists online, you can check it out. Like I said, if you have a hard time sleeping on Friday night, just pop that thing open. All night at the bar, pop that open, you'll be gone. Alright? It's not important. What's important is how do we use that curve? In order to understand that curve and its characteristics, you have to know calculus. Well, there's no calc prereq for this course, right? No, there is not. So what we're going to do in the last 20 or 30 minutes or so of this class is explain this to you in a non-calculus way. I want to show you in a non-calculus way how Carl Friedrich Gauss's curve, actually Abraham de Waal is the guy that actually discovered it. I don't know how Carl Friedrich Gauss got credit for this. Pythagorean theorem you've all heard of, right? Who discovered Pythagorean theorem? The Chinese, 1,000 years before Pythagoras. How the hell did that Greek get his name attached to it? Who did he sleep with? I don't know. Who did he sleep with?
He published.
He published, the bastard.
He got the word out.
Carl Friedrich Gauss did not develop the bell curve. Abraham de Moivre did. De Moivre gets his name on a penny. Carl Friedrich Gauss gets his name and his picture and his curve. And de Moivre's curve on a $10 bill. I don't know. It's academia. It's a tough world out there. It's a tough world. I think I'm going to tell you that. What I came here to do was to draw some parallels between where you already know very comfortably and what you're about to